Let's find an equation that completely describes a wave. An expression that tells us the amplitude of the wave for every position and for every time. We already know that for a simple harmonic oscillator, the position along the axis of motion is given by the amplitude times the cosine of omega t plus some constant phased phi. But that describes the position of a one-dimensional motion. Here we want to describe the motion along the direction of propagation of the wave, but also along the direction of the perturbations. If we imagine a generic wave and take a snapshot of it, we are assuming sinusoidal waves for simplicity. With this, we will be able to measure the wavelength of the wave and the amplitude of the wave. We also know that after a time equal to the period of the wave will have the same shape. This will happen periodically in space. To describe this sinusoidal shape, we can write that the height y is equal to the amplitude a times the sine of some argument that will change as we scan the x-axis. Let's find this argument that goes inside of the sine function. This argument needs to be something that repeats every time that we complete one full wavelength. The distance between two maxima is lambda. The distance to x divided by lambda is the portion of distance compared to the wavelength. When x is equal to lambda, the argument of the sine needs to be 2 pi, so that we repeat the value every wavelength. Then this is sine of 2 pi over lambda times x. This is the equation that describes the height of the wave as a function of the position. But this is not the whole story. We want to have an equation that describes the height of the wave also as a function of time, because the wave propagates in space and time. Because the wave moves with velocity v and travels a distance vt, we can complete the wave equation as. We define the wave number k as 2 pi over lambda, so that, and because the velocity is the wavelength over the period, writing lambda in terms of k, and because the frequency is 1 over t, and because omega is 2 pi f, y of x and t is equal to 8 times the sine of kx plus or minus omega t. The plus or minus signs indicate the direction of motion of the wave. Just verify yourself that the negative sign indicates moving to the right and the positive sign indicates moving to the left. To generalize this equation to any initial conditions, we add the phase factor phi. This, as with the simple harmonic oscillator, will consider where we have the origin of coordinates with respect to the wave. May science be with you.